We are continuing module 6. In this module, we are discussing construction of ultrafast laser. In the previous slides, we have already understood different elements which are used in the laser oscillator, ultrafast laser oscillator. We have dispersion compensator given by two prisms, high reflector, we have self mode locking done by this aperture and the gain medium and the laser cavity with the help of these two mirrors and the output coupler. So, this kind of laser oscillator, this kind of ultrafast oscillator can produce energy in the range 5 to 10 nanojoule per pulse. Now, question is, if we need more energy, what to do? Definitely we have to amplify the pulse. Due to this high peak intensity, ultrafast pulses cause local heating at the bulk or surface of the gain medium, resulting in thermal fracture, decomposition, melting of the gain medium. The surface damage threshold, however, varies based on thermal diffusion, how quickly the local heat is dissipated over the bulk of the optical element. Nonlinear self-focusing, on the other hand, causes bulk damage when high intensity ultrafast pulse propagates through the optical elements. Therefore, amplification of output beam of the ultrafast laser oscillator is not a straightforward task. How can the deleterious effects of high peak power be avoided during amplification stage? Nearly all high power ultrafast laser systems make use of the technique called sharp pulse amplification, CPA. What does it mean? It has 3 steps. Step 1, the pulse which is coming from the oscillator, which is less intense pulse, first needs to be stretched so that the peak power can be reduced, and peak power is defined by energy per pulse E divided by delta T. Delta T is the duration of the pulse, and we remind duration of the pulse is defined as a full width half max of the intensity profile. So, what we have done, we have to do step 1, we have to stretch the pulse so that the peak intensity can be dropped. Then you amplify the pulse and then recompress the pulse. This is step 2 and this is step 3. So, this scheme is called sharp pulse amplification. CPA scheme can increase the energy of a short pulse while avoiding very high peak powers in the laser amplification process. This is done by lengthening the duration of the pulse being amplified. By lengthening the pulse in time, energy can efficiently be extracted from the laser gain medium while avoiding damage to the optical amplifier. CPA is particularly important for efficient utilization of solid state laser gain medium with high stored energy density. This scheme can provide energy per pulse as large as 10 joule per square centimeter. But before injection into the amplifier, short pulse needs to be stretched in time by introducing a frequency chirp into the pulse. which increases the duration of the pulse by a factor of 10 to the power 3 to 10 to the power 4. The duration of the stretched pulse is determined by the damage threshold of the optics and nonlinear distortion of the spatial and temporal profiles of the beam. As discussed in earlier module, a sharp pulse can be obtained simply by propagating a short pulse through optical material such as glass. So, we have already seen that material dispersion and particularly second order spectral phase can actually introduce chirp or broaden the pulse. So, if I have a short pulse, it can be broadened like this, material dispersion, and it is positive GVD which is responsible for this kind of dispersion, for this kind of pulse broadening. However, to increase the duration of the pulse by a factor of 10 to the power 3 to 10 to the power 4, which means if I have femtosecond pulse, I have to get picosecond pulse. So, the broadening has to be 10 to the power 3 times. The dispersion brought about by pulse propagation through simple optical material is not sufficient, because we have seen that only GDD of a material is very small. So, we need certain kind of optical elements which will introduce a big amount of positive GDD of the order of 10 to the power 3, a factor of 10 to the power 3. In this case, a grating pair is very suitable. A grating pair provides necessary high dispersion that is required to stretch a pulse by a factor of 10 to the power 3 to 10 to the power 4. We shall come back to this. So, here we have shown two different arrangements, Martinez geometry and Stress's geometry. These two geometries, if you look at these two geometries, we are using grating pairs to introduce the chirp or broadening the pulse, but we will discuss this shortly. Before we do that, we have to go over the grating equation. Need to understand the property of a grating. A diffraction grating is an optical element that possesses an arrangement of a large number of parallel, equidistant and closely spaced slits of same width which are placed side by side. So, this is called, so if I have a flat surface, we prepare slits like this, we make grooves, and this surface becomes grating surface. Slit sizes are comparable to the wavelength of the light. Diffraction gratings are manufactured by ruling or drawing lines on a well polished thin uniform sheet of glass or reflecting metal surface. The number of grooves which are drawn may vary from 15,000 to 30,000 per inch or even more. The grooves scatter light and acts like opaque substance, while undisturbed polished parts behave like slits. Similar to prism, a diffraction grating disperses light composed of different wavelengths into light components by wavelength. Diffraction gratings are usually of two types: transmission grating and reflection grating. As reflection grating find numerous applications in ultrafast laser system, we shall briefly discuss dispersion of reflecting grating. As depicted here, there are two different configurations we have shown. They differ by how the incident beam and the diffracted beam are with respect to the surface normal. So, the first figure, figure number A, we see that with respect to the surface normal, this dotted line, A the input beam and diffracted beam, they are on the same side. On the other hand, in this figure B, input beam and diffracted beam are on the opposite sides with respect to this surface normal of the grating. Alpha is incident angle and theta is diffraction angle. Now, if we look at A and B, these two rays, then we see that in order to have constructive interference after diffraction, the beam which is this A beam, diffracted A beam and diffracted B beam, in order to have this constructive interference between these two beams, the extra path length travelled by A, that is this distance plus this distance, this extra distance is travelled by A, and in order to have this constructive interference after the diffraction, we need to have this extra distance to be n lambda. Then only we get this constructive interference. And d sine alpha plus d sine theta is representing this extra distance from here to here and here to here. Similarly, if we look at this geometry, we get another equation. These equations are characteristic equations of grating. Here d is spacing between slits and 1 by d is representing n, which is the number of slits per unit length, and n is order of diffraction, lambda is the wavelength. So, if we consider a constant alpha, if it is constant alpha, so for constant alpha, we can say that sin theta is proportional to lambda. Sin theta is proportional to lambda. So, in this configuration A, we see that theta and alpha are on the same side of the grating normal, and in that case d theta d lambda, this derivative is going to be always positive. But on the other hand, here for this configuration, where configuration B, where alpha and theta are on the opposite side of the grating normal, for that, for constant alpha, we have minus sin theta, which is proportional to lambda. So, this d theta d lambda is going to be negative. So, to remind or to remember whether this d theta d lambda would be positive or negative, we have to just remember that whether the beam, incident beam and the diffracted beam are on the same side of the normal, surface normal, or they are in the opposite side of the surface normal. So, this is the feature of a grating, and given this information, if we again take a look at the stretcher or compressor, in which we use grating, we'll be able to understand its action as well. In Martinez geometry, Martinez demonstrated that by placing a telescope between a grating pair, the overall dispersion or lengthening of the pulse can be controlled by the effective distance between the second grating and the image of the first grating. Here, in the first configuration, we have two lengths of focal length f, and these two lengths are placed 2f apart to form a telescope. Now, if an object is placed at f in front of the first lens, an image is formed at the distance f behind the second lens, and that's exactly where two gratings are placed. So, two gratings are placed at this focal lengths, and if we place them, the net dispersion remains 0. So, even the pulse, a short pulse is entering this optical arrangement. When they are coming out of it, we do not introduce any dispersion. The same pulse will come out, because this red light and blue light representing lower frequency and higher frequency regime of a pulse. So, what will happen, this lower frequency components and higher frequency components will have the same optical path length, they are traveling the same distance, and that is why there is no effective chirp introduced in the pulse. Now, if we push the second grating towards the lens to a distance f minus delta f in this configuration. So, this was the previous focus point where the grating was previously. Now, we have pushed this grating towards the lens, and if we do that, what happens, blue ray, which means high frequency components, travels longer path. Here we look at this, incident beam and diffracted beams are on the opposite side, and that is why d theta d lambda is going to be negative. If it is negative, which means higher frequency will bend more, will have, so higher frequency will bend more and lower frequency will bend less, and that is why we get red color propagating along this direction and blue color propagating along this direction. But if we look at the relative path distance or the path difference, we see that the blue light is traveling extra distance as compared to red light. So, and this is introducing positive GVD, because red component will come out of this cavity first. So, the earlier phase or the earlier time is represented by the low frequency components of the pulse, and later time of the pulse is represented by the high frequency component of the pulse, and this is nothing but positive GVD. We have introduced positive GVD, that is why we have introduced chirp and we have stretched the pulse. Now, if we look at stresses geometry, what happens when a pulse entering a pair of identical parallelly dispersed grating. So, we have two gratings facing each other, but they are parallelly displaced. Two gratings are parallelly displaced, and Here alpha and theta are on the same side of the surface normal. That's why d theta d lambda is going to be positive, which means red light now will bend more and blue light will bend less. And in that case, red light is now traveling longer distance when they are coming out of this arrangement, and blue light is traveling shorter distance. And that's why in the early time of the pulse we get blue components, and later time of the pulse is contributed by the interference of the low frequency components. And this is the way we can introduce again a chirp in the pulse. But now imagine if we consider Martinez geometry and we have a pulse, a short pulse going through Martinez configuration, that is called stretcher. Then we introduce this chirp, and then if we send this pulse to the stresses geometry, we get the reverse of this effect, which means we recompress the pulse again. This is why the basis for a perfectly matched stretcher or compressor pair is to introduce right sign and factor for GVD. Stretching and recompression with grating pairs, either using Martinez configuration or traces geometry, thus allow large and reversible stretch factors or compression factors. So we can use this as stretcher and this configuration as compression. Amplification of chirp pulses is done by titanium doped sapphire, a material having very desirable characteristics, very high damage threshold, high saturation fluence, high thermal conductivity. Therefore, pulses with an energy greater than 1 joule can be extracted from a relatively small diameter rod, let's say 1 centimeter. Therefore, pulses with an energy greater than 1 joule can be extracted from a relatively small diameter rod, sapphire rod, 1 centimeter by 1 centimeter it could be. It has also broad absorption maximum near 500 nanometer. Absorption maximum, which means that if I use a pump laser to create the population inversion, again we can remind that this is a 4-level system. So I need a pump with higher frequency and it will give stimulated emission at lower frequency, and that's why it gives stimulated emission at 800 nanometer, and pump is used for 500 nanometer. Since the sapphire host is birefringent, this crystal must be cut so that both the pump laser and amplified pulse polarization are along the crystal optic axis. There are two different types of amplifiers we have, but before amplification we have to remember that we have an oscillator. This oscillator produces low energy pulses, very short low energy pulses, and then we have to stretch the pulse. We need a stretcher. And once we have stretched the pulse, stretch pulse is always a sharp pulse, and then we have to send it to the amplifier. After amplification, we have to again recompress the pulse. In the amplifier, we simply amplify a sharp pulse. And then we recompress the pulse again. So in the amplification stage, we can use two different kind of amplifiers: regenerative amplifier and multipass amplifier. Regenerative amplifier, the difference between these two amplifiers is in regenerative amplifier we use a cavity, but in multipass amplifier we do not use a cavity. The low energy sharp pulse is introduced to the cavity in this regen amplifier using a time gated polarization device. That's called here such as Pockels cell and a thin film polarizer. The pulse then makes many round trips through the gain medium, at which point the high energy pulse is switched out by a second time gated polarization gating. So one time gated polarization is used to introduce the pulse, then second time gated polarization rotation is used to take the amplified pulse out from the cavity. On the other hand, in the multipass amplifier, beam passes through the gain medium multiple times without the use of cavity. So we have input beam coming this way, it's making one trip through the crystal, then it is reflected here, it's getting reflected. So the first round trip comes here, getting reflected here, is going here, then again is coming here, and multiple times it undergoes and then it comes out of the cavity like this. In both amplifiers we have to use pump, which is used for 500 nanometer excitation to create the population inversion, and the seed beam is the input beam coming from the oscillator. So this comes from an oscillator. Also this input beam comes from an oscillator. So with this we have come to the end of this module. In this module we have studied construction of ultrafast laser, different properties of ultrafast pulse propagation have been discussed, and those properties have been used to think about how to build an ultrafast laser. We have discussed population inversion, we have discussed 4-level system, we have discussed longitudinal modes, mode locking, dispersion compensation, and finally we have discussed the scheme of chart pulse amplification. We'll meet again for the next module.